Hello everyone, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Today we're going to talk about the exploding stars, the biggest stars in the universe, how they live, how they are born, and how they die. Again, let's go back and we can go back and look at the fiducial idea. The top area shows exactly how the sun evolves from a protostar. It has a long main sequence lifespan of about 10 or 11 billion years. It swells up into a red giant, puffs off its outer layers with a planetary nebula, revealing the core as a white dwarf. And we see these things from the left-hand side, which is a star-forming region with a Horsehead Nebula in the middle. And then in the middle picture, we've got a globular cluster in the lower right and a beautiful open cluster in the open left, which is the remnant of a new batch of stars. And over on the right is the Ring Nebula, which is a planetary nebula surrounding a tiny, tiny, tiny white dwarf star that illuminates it and causes it to glow by ionizing. But that's a story for stars like the Sun that live about 11 or 12 billion years. We're going to look at more massive stars. Hot stars, like O and B type stars, basically their masses are greater than about 4 solar masses. They burn extraordinarily hot. They live extremely fast lives, and they die very young. So their main sequence phase, they do burn hydrogen into helium in their cores just through a different process, not the proton-proton chain, but through the CNO cycle. They also build up a helium nugget in the core for their main sequence phase, because that's the definition of a main sequence phase, is hydrogen to helium burning. And they do this just like any other star. The main sequence is where stars burn hydrogen into helium. But for high mass stars, this lasts at most about 10 million or so years. So let's look at one of the more fiducial stars of this type in the sky. You know it by sight in the stars, but this is an artistic view of the star Betelgeuse. And Betelgeuse is a nearby supergiant red star in the constellation of Orion. This is a beautiful piece of artwork by El Calzada at European Southern Observatory. And this is a wonderful picture by Babak Tafrishi of the constellation Orion above the Very Large Telescope Array down in Chile. And so what we see is we see the belt of Orion up there, and because we're in the southern hemisphere, Orion's inverted. So just above the telescope, the bright red star is the star Betelgeuse. And Betelgeuse, this is a picture, is a massive, not an artistic picture, but rather this is a massive array of pictures put together as a mosaic by Rogelio Bernal Andreu, and it was featured in Astronomy Picture of the Day in 2010. So Betelgeuse is the upper left shoulder of the giant of Orion. And there's all sorts of wonderful things going on in the Orion Nebula and the Orion area of the sky. But Betelgeuse is the star we're going to be talking about. Betelgeuse is a red supergiant star. It lies in the upper right area of the HR diagram with a spectral type of M and a luminosity of about 100,000 times that of the Sun. And it's about the same temperature as little red dwarf stars on the main sequence, or giants like Aldebaran, but it's much, much, much larger. And Betelgeuse is brighter, and we call it a red giant because it's brighter at red wavelengths compared to blue wavelengths of light. And so this is a sample type M-type star that we might get from I forget exactly where, I grabbed this from the Sloan Digital Sky Survey. And this particular thing shows an M-type star, and the wavelength band is from 4,000 angstroms to 7,000 angstroms, which spans the visible light. So to your eye, this is the part that is visible to your eye. And so I kind of grayed out the rest to the right. But you can see it actually glows a lot in the infrared. But for visible light, it's brighter in the red wavelengths than it is in the blue, and has striking absorption features and so forth. And because it's bright in the red compared to the blue, that's why it looks red in the sky. Now we can also judge whether it's a giant or a main sequence star by looking at these absorption features of the dips from the continuum. You can imagine that this is actually some sort of continuum that goes over the top with lots and lots and lots of dips that go through. So where the peaks are is where the continuum is. So you could draw a line across the peaks of the continuum and then imagine that it's actually that the absorption lines are huge absorption lines down from the peaks, where the peaks go up to the continuum. And so you see they're very, very, very wide peaks, very wide absorption features. And if they're comparatively narrow lines, when there's only one or two, then it's called a giant star. And if they're wide absorption lines, then it's a main sequence star, because main sequence stars are compact. So therefore, they have a lot more Doppler broadening. The atoms and molecules are moving faster, so therefore the widths of the lines are broader. And in a giant star, the widths of the lines are narrower because the pressure is lower. And because the pressure is lower, there's less movement of the atoms, and the atoms can only absorb it there near the frequency where they're absorbed. But if they have high pressure, they're moving faster, and so you can get Doppler shifts for the absorption. Anyway, so from the spectrum, which gives you the line widths, and the color, which gives you the temperature, you can deduce that this is a supergiant type star and of spectral class M. Now, how do we know it's really that big? I mean, what we can do is, remember, we can also take, if we have a handle on the luminosity, remember there's a luminosity relationship, or the Stefan-Boltzmann relationship, where the luminosity is equal to the surface area times the temperature to the fourth power. So if we have a way of measuring the absolute luminosity of it somehow, and then we know roughly its radius, then we know its temperature, which is obvious from the spectrum, then we can determine its radius and determine it's an extraordinarily large star. And that's the Stefan-Boltzmann relationship. Anyway, we do know that Betelgeuse is an extraordinarily rare star because it's a more massive star than the Sun. So roughly less than a couple of percent, like 2 to 4, like almost 3 or 4% of the stars in the sky are even as or could be as massive as Betelgeuse. Actually more like about 1%. So Betelgeuse is probably much more massive than a 2 to 4 solar mass star. So we're really looking at the deep, deep, deep little blue sliver where we have a 4 to 8 or 10 solar mass type star, which is about 1% of all the stars in the sky. And Betelgeuse falls in that realm. It's not one of the small mass stars between 1 and 2 or a half or a quarter or less than a quarter the mass of the Sun. It is in that elite category of very, very, very massive stars where so few of them in the sky are that massive star. Now, Betelgeuse is about 152 parsecs away, or about 500 light years, and the luminosity is about 120 times that of the Sun. So it's extraordinarily luminous. And that puts it, this is really fun statistic. The absolute wattage is about 4 times 10 to the 26th watts. And if you compare that to what human civilization puts out, which is about 17 terawatts, we're nothing compared to the luminosity of Betelgeuse. We're nothing. 10 to the 14th times less. Oh my goodness. And the Betelgeuse itself is about 1,200 times that of the Sun. That comes from both direct measurements, as we'll see in a second, as well as the Stefan-Boltzmann relationship. And we know that 100 Earths fit across the Sun, but about 120 Earths fit across Betelgeuse. That means that it's bigger than the orbit of Jupiter. All right, so let's take some interesting looks. This is a 7 millimeter radio image taken with the Very Large Array down at NRAO, and it was taken in 1998 by Lim, Corelli, White, Beasley, and Marson. And they found that the optical disk of Betelgeuse is this roundish sort of thing in there. But the glow that we see here is a radio emission. Radio emission from Betelgeuse's very diffuse atmosphere. We see that Jupiter's orbit would easily fit inside of this atmosphere of Betelgeuse, and so Jupiter would slowly spiral in. And we see that another thing about Betelgeuse, it's not spherical. It's not a spherical star. So people thought, wow, that's really interesting, 1998. So following up, and prior to that, Betelgeuse was measured in terms of its physical size with the Hubble Space Telescope image of a direct imaging by Dupré et al. At Center for Astrophysics using the Hubble Space Telescope. And this is a direct image of Betelgeuse. We see that the star is actually quite large. It's much larger than Earth's orbit, much larger than Jupiter's orbit. So Betelgeuse is this enormous, physically large star. Now, a group at the European Southern Observatory took a series of images and then placed them inside using the VLT and infrared imaging as well as optical imaging to try to determine the actual dimensions of it. And if we take the little red dot that's in Dupré's image from before, it would just fit inside that red circle, just barely. And you can see that there's kind of plume-like structures that are visible in the infrared. Now, the right-hand side, this plumy sort of thing is an infrared image. Remember these types, as we saw gently in the other spectrum that we saw before, that the vast majority of the emission from this star is actually in infrared. So because it's a cool, large star, and since it's cool, the dominant radiation is infrared. Well, it's also puffy. There's a plume shooting off to the side. There's also other plumes kind of noodling around. It's a really distorted thing, and it's not actually spherical the way we think of this, like the sun. The sun is spherical, but we can really think of Betelgeuse as not even spherical. It's just this puffy sort of thing. And it's an incredibly sharp image. This was taken by the Very Large Telescope in Chile, which is that set of telescopes that we saw from Babak-Tafrishi's image from before. And we're actually seeing this unknown plume to the right. What's funny is the individual pixels are as small as 37 milliarcseconds, which is about the same size as a tennis ball viewed from the ground at the International Space Station, and is all near-infrared imaging. And if we then zoom out with a different infrared camera, again with the VLT at ESO, we see the black disk is the thing that is used to occult the star because the star is incredibly bright. It's one of the brightest stars in the sky. And so to actually get the image of material surrounding it, you need to actually block it out. And the previous image was put in the center, and the disk-like image that we see from Dupre's images is the red circle in the middle. And now we zoom out to show the full grandeur of Betelgeuse, which really doesn't actually seem like much of a star anymore. It seems like a star nebula thing sort of thing. And if you actually were to take a spaceship and fly over near Betelgeuse, you would find that you'd fly into this cloud-like structure that got brighter and brighter and brighter towards the center. You'd fly by globs of mass that's moving out with enormous winds that would buffet your spacecraft as you tried to get closer and closer. And eventually you'd find yourself in an incredibly bright, foggy mist and get closer and closer to the star. And you would just all of a sudden be close to what would be bright enough that we would call the photosphere. So many of the absorption features that are found in Betelgeuse's spectrum come from this expanding shell of gas that comes off of the star itself. So Betelgeuse is shedding a lot of mass. And just like we saw last time in the low mass stars, how we had a star like the sun puffs itself apart and forms a planetary nebula, Betelgeuse isn't waiting. It's not done yet with its life before it starts really puffing itself apart as all high mass stars do. And that means because it's puffing and moving, it's variable. So it's an actual variable star, which is easily seen with binoculars. So if you want to go out in the night sky and take a pair of binoculars and see what the variation in magnitude is, this has come from the American Association of Variable Star Observers. This is their data, and it's compiled by a number of observers. And these observers then submit their data to the AAVSO. You can become a member too. It doesn't cost you. Well, it costs you a little bit, like $20 a year. But then you get to submit your data into this set, and you can make meaningful science measurements just with binoculars, specifically of this star. But as you can see, the star varies as time progresses from left to right. We see that the brightness and magnitudes varies pretty big. It can vary up to a magnitude in brightness. As you can see, roughly about 2008 or 2009, it was pretty dim, and then it brightened it went as dim as magnitude 1, and by about a couple years later, it was as bright as magnitude 0.01, almost a zero magnitude star, and it's been brightening and dimming by about a quarter of a magnitude fairly regularly as it puffs itself apart. So Betelgeuse is an extraordinarily variable star, and it's fun to observe. So I would invite you to use this as one of your primary variable stars if you want to observe them and do some science in your own home. This is a great way to do it. And you can learn how to do this by going to the American Association of Variable Star Observers. You don't have to become a member to submit your data, but they always appreciate that you do. All right, so stars themselves can be extraordinarily big, as we've seen in the past. The sun is only about 700,000 kilometers across. And so on this image, it's really tiny. And the bright star Arcturus, which is in the constellation of Bootes, is much, much, much larger than the sun, almost 20 times larger, 30 times larger. About 30 times larger. And if we then look at the red supergiant Antares in Scorpius, it's extraordinarily large, larger than the orbit of Mars. And so these are the red supergiants. So red supergiants exist like Betelgeuse. So how do they live? Well, they're so big, they're so massive. So a large physical star like a red supergiant, doesn't mean it starts like that. It started as a main sequence star and swelled up. But while it was on the main sequence, it burned hydrogen to helium. But it does not do so. But these massive stars, any star more massive than about 4 times the mass of the sun, does not use the proton-proton chain to fuse hydrogen to helium. It uses the CNO cycle. It does fuse 4 protons. You can see the equations. These are a set of reactions where a proton P combines with a carbon-12 nucleus. They collide together, and the arrow says the output is a nitrogen-13 or a light nitrogen nucleus, and that emits light in the form of a gamma ray. That's what that little YE sort of image is. That's a gamma ray. The next step is this light nitrogen nucleus. Then beta plus decays, which means that one of the protons turns into a neutron and therefore emits a positron and a neutrino. This can only happen inside the nucleus of an atom. It can't happen as a free proton, but there it is. Of course, then the positron interacts with an electron to form a gamma ray as well. But then the carbon-13 then collides rapidly with another proton, which forms nitrogen-14. So we're back to nitrogen again, and that emits light in the form of gamma rays. And then that nitrogen gets slammed by a proton, and it forms oxygen-15, which itself is radioactive and unstable, falls apart to nitrogen-15, which is briefly stable, and that emits again another positron and a neutrino, and then that gets slammed by another proton, and that forms the chain, which returns it back to a carbon-12 nucleus, and that spits out a helium nucleus. So we can add all this stuff together. Basically, 16 objects. So the proton could be something about 1 in the upper left. So 16 things go together to make a carbon-12 and a helium. But notice that the carbon-12 acts as a catalyst. It returns back to the beginning of the cycle, having been used up, and the intermediate processes of creating nitrogen and oxygen along the way, so it doesn't really go anywhere. So it acts as a catalyst. And that catalytic reaction keeps the carbon going, and this is an incredibly important element. So for the sun does a little bit of this. About 2% of the sun's output comes from this. But once you get above 1.1 solar masses, or just a little bit more massive than the sun, CNO is about 50%. But once you're up to about 4 solar masses, it is 100%. So by 2 solar masses, you're doing a CNO cycle completely. Now, this is, of course, inefficient, but it's really interesting to return to the idea that what does fusion energy give you? Remember, when you fuse 1 gram of hydrogen into 0.993 grams of helium, it loses mass. Some of the mass of the 4 hydrogen nuclei, those 4 protons, gets converted into energy. Less than 1%, about 0.7% of a gram gets converted into energy. And for every single one of those things, that provides 6 times 10 to the 18th ergs, which is a large amount of stuff. And that's a huge amount of energy by comparison. Just to do this one interaction, that was enough energy to lift about 30,000 tons, 64,000 tons of rock up to a height of 1 kilometer. So basically, just fusing 1 gram of hydrogen into helium is enough energy to take a building and throw it into the air about 1 mile. That's what fusion energy gives you. So if someday we can figure out how to do this safely and efficiently, we could replace pretty much all of our energy needs with fusion if we can figure out how to do that, which would be pretty cool. Anyway, so just like low mass stars, no party lasts forever, and every star, no matter what is big or small, population 1 type stars, which are young stars that have come through reprocessed material, have roughly about, by abundance, is about 10% by numeric abundance, is helium, but then about 90% by abundance, meaning the number of particles, is about 90% of the particles are hydrogen. And about 5 billion years into its life, the sun has only converted about 10% of its hydrogen in the core into helium. And by about 10 billion years, the sun specifically, now we're not talking just going back to the sun just to get reference frame, the sun will have converted all of the core material to helium, and a significant fraction, out to about half the star's core, will be helium. Now, that's what happens in the sun. A very similar thing happens in every main sequence star. It builds up this nugget of helium in the core, and when that runs out, it's over. And it doesn't matter whether it's using the proton-proton chain, which is the upper left, or the CNO cycle, which is the upper right. Those are the two dominant ways that hydrogen gets fused into helium inside of stars on the main sequence. That's the way it's done. There's other things then will come later, which is the triple alpha process. We described that when we talked about the sun, when the sun started dying, and that happens too. But even that doesn't last. Helium fusion doesn't last because you run out of stuff too. Anyway, so what will happen to a massive star that is way up the main sequence, that's an O and B type star, when it starts to run out of fuel and it uses up its hydrogen in the core? Once it's exhausted, it does the same dance that the sun would do. The inert helium core contracts down and starts heating up. There's again the hydrogen burning shell around it and around that contracted core, because pressure, gravity pulls the star together, and it just gets compressed and hotter, but it's not participating in fusion because it's not hot enough yet. So hydrogen burning or hydrogen fusion is in the shell around that nugget in the core. And then this huge puffy envelope expands. So these red supergiants, unlike the sun, which just kind of lazily goes up, no, these shoot straight across to supergiant phase, and they get enormous, radically enormous in a very short period of time, less than 1 million years. Now, the funny thing is, along the main sequence, stars don't have a huge radius difference. Pretty much an O-type star in the main sequence is just only a little bit bigger than the sun on the main sequence. The radius isn't that much bigger. But once a massive star runs out of hydrogen, it swells up much larger than the sun will ever get. The sun will never become a supergiant, it'll become a giant star. But these stars become supergiants. Eventually, this supermassive star gets the core temperature raises to about almost 200 million Kelvin. That's enough to start up helium burning. And helium burning through the triple alpha process, as we showed before, that makes carbon and oxygen. That only lasts, we're in the sun, this would last about 1 billion years. For massive stars, it lasts about 1 million years or less. And then we've got this layering set that happens down in the core, where there's helium burning in the core, then there's hydrogen burning around, and notice that there's no helium flash, because now it's going to be there, when it ignites it smoothly. Stars more massive than about 2.5 times the mass of the sun don't have a helium flash, meaning the electrons do not get so compressed in the core that they become degenerate. And the degeneracy never occurs for stars more massive than 2.5 times the mass of the sun. And it starts burning very, very, very gradually. So much more massive stars simply wag back and forth, and they get bigger and smaller, hotter and cooler, and they stay at that extraordinary luminosity, but their surface temperature changes. Now remember, the HR diagram shows the surface temperature. So the surface temperature of a supergiant star ranges between, say, 3,000 Kelvin and maybe 20 or 30,000 or 10 to 20,000 Kelvin. That's a blue supergiant. A blue supergiant isn't really that blue. It's more whitish because it's kind of the same temperature as an A star. But I guess an A star is kind of bluish. It will be bluer than the sun. In any event, it becomes a blue supergiant when the helium ignition starts, and then it smoothly moves back into this new framework. So that's producing more energy, which is producing a little bit more luminosity, but that allows the star to actually collapse back down. All right, so when the helium finally runs out in the core, and that doesn't take long, it takes an extraordinarily short period of time. In fact, it doesn't get down to the horizontal branch at all. It just kind of wags back and forth. When it runs out of helium in the core, then the carbon and oxygen core collapses and heats up. And that's a big deal because now the hydrogen helium are burning in shells around it, and it becomes a supergiant again. So it does this whole dance all over again. Notice how the size of the star is dependent upon what's happening down in the core. When the star grows in size, it grows in luminosity. And it's growing in luminosity because the energy output that must occur is getting very, very, very high in the core because there's no new energy source. It's contracting under gravity. It's running out of fuel. The atoms and molecules, the atoms, they're not even atoms, they're just ions. The nuclei have to move insanely fast in order to find other nuclei that they can fuse with, because they're running out of sources of things to hit. So therefore the temperature has to rise. When the temperature rising means that the particles are moving faster. And they have to move faster because they have to go farther in order to find something, in order to hit, in order to make the fusion. So that's kind of what's happening. So eventually the carbon-oxygen core continues to collapse. It gets smaller and smaller, and that releases more heat by gravitational collapse, because as you collapse a gas, it releases the heat, and eventually the core temperature exceeds 600 million Kelvin, and then the density is insanely large. It's about up to 150,000 grams per cubic centimeter, which is 1,000 times more dense than lead or gold. So a typical gram, a cubic centimeter of gold might weigh a kilogram, but this star, which is a gas, will weigh 150 kilograms per cubic centimeter, and it's still a gas. It's just really bizarre. It's not a solid, even though it's much more dense than lead and gold, 1,000 times more dense. Finally, we can get to the point where carbon fusion can occur. And then we get all sorts of reactions. Carbon burning is a new set of reactions that happen for much more massive stars that are much more massive than the sun. Carbon can slam into another carbon nucleus, and that forms magnesium. Neon can slam into helium, and oxygen can slam into two helium nuclei, and that builds up an oxygen neon magnesium core. Now, the oxygen neon magnesium core is also inert because it's not hot enough to fuse oxygen into anything heavier than that. And so carbon 12-12 fusion creates the products of magnesium, or neon and helium, or oxygen and helium. Those are its byproducts when carbon 12 smacks into another carbon 12. This doesn't release a lot of energy because, remember, it takes a lot of energy to make them initially, and each larger nucleus that you get gives off less and less energy. So you got to do more of it, and there's less of it to do. So you have to do more of it. There's less of it to use because now we're knocking together fewer objects because they're all combined together, and you get less energy out of it. So this can't last long. And so the reaction rate must be higher so that it can stay, so the star can stay aloft. So carbon burning can only last about 1,000 years before it runs it out. And that's roughly where Betelgeuse is now. We think that Betelgeuse will one day explode in a supernova, which I'll talk about later and next time, but it might be within the next 1,000 years or 10,000 years or a million years. So where Betelgeuse is now, it has an inert oxygen neon magnesium core. Very rapidly, there's a carbon burning shell happening fantastically quickly around it. Above that it's hot, and there's nothing in there except that. The helium then mixes through, and that creates helium burning in the shell around that, and whatever protons are left that are just on the boundaries of that burn and fuse hydrogen into helium. So the helium burning shell makes helium, which descends into the helium burning shell, which makes carbon, which descends into the carbon burning shell, which then when carbon burning creates oxygen, neon, and magnesium, which descends below. And all above the supergiant envelope, it's very, very, very unstable below. It's puffing off its outer layers, just like we saw initially with Betelgeuse just puffing itself apart, because the interior is extremely violent place. So carbon, oxygen, neon, magnesium core is about what stars between the masses of about 4 and 8 solar masses will ever do. That contracts and contracts and contracts. That core of oxygen, neon, and magnesium contracts, and that contraction releases even more heat and that pops the entire and creates those shell burning around it, which is incredibly unstable, which pushes the star apart and makes it froth. Now, these are the low-end masses of stars that will end up making what we call Cepheid variable stars. Cepheid variables run between about 5 and 20 solar masses, and Cepheid variables will become incredibly important when we study the Milky Way and we study how we can find the distances to the cosmos. So these are the progenitors, and this is the time of life where some of these massive stars become Cepheid variables, when they pass back and forth into the upper left area of the HR diagram above the main sequence. So these kinds of stars eject all their stuff, and we saw, just like we saw Betelgeuse doing, and they leave a white dwarf behind, just like we saw with the sun in the previous thing. So a massive, super heavy-duty stellar wind coming off and leaving a core behind, a white dwarf core with a large planetary nebula. Much more massive than that, at least 8 times the mass of the sun. Then carbon burning can happen. The carbon burning evolution is insanely quickly. It'll happen less than 1,000 years. And the star's envelope has no time to respond to that. And there's a big thing that's going to happen really soon. However, there are incredible strong stellar winds that can be shown, that are evident from these massive stars, and they can erode the outer envelope, pushing it outward, making enormous bubbles and burbling appearance to the star. And Eta Carina, which is one of the great examples of such a massive star much more massive than 8 times the mass of the sun. I believe that Eta Carina is about 20 to 40 solar masses. And we see from this Hubble Space Telescope image of the nature of this particular star, which is Eta Carina, which is clearly undergoing some violent stuff. These bubbles demonstrate that the star is incredibly variable. It's puffing off its outer layers incredibly violently. And this can't last, of course. And so this star is in the course of dying, and very, very, very soon it will do something very catastrophic. And one that, when Eta Carina finally goes supernova, you will be able to read by it at night. So for much more massive stars, the oxygen neon magnesium core contracts and contracts, and by contraction it releases gravitational energy. Gravitational potential energy then heats it up to 1.5 billion Kelvin. I mean, how do you even get past what that is? Okay, I really can't give you a handle on what 1.5 billion Kelvin is like, but let's just say it's bloody hot. And the density is now about 10 billion grams per cubic centimeter, or 10,000 kilograms per cubic centimeter. These are extraordinarily rare conditions. Remember that massive stars, extremely massive stars, make up the most rare of all of the stars in the cosmos. So even though they're incredibly bright, they're quite rare, with far fewer than 1% of the stars in the sky will ever do this. So neon, I'm not going to really go through all the reaction rates because now they get extraordinarily complex. And when neon burning occurs, it will create more oxygen, more magnesium, and lots and lots and lots of other heavy elements. Now we're below the element iron. Now, a lot of these reaction networks, remember the carbon, nitrogen, oxygen created neutrinos, as well as all of the carbon burning that created the oxygen, neon, magnesium. That created enormous numbers of neutrinos, and now most of the luminosity of the star becomes in neutrinos itself. And the star rapidly creates this core, and neon burning can only last a couple of years before it runs out. But neon does not it provides even less energy than the previous step. And so there's fewer particles, it provides even less, the temperature is even higher, so the reaction rate is even faster. Neon is done in a couple of years. When you're done with that, well, what the heck? What's next? Well, you burn oxygen. Oxygen then starts fusing, and the temperature rises rapidly into about 2 billion Kelvin, and the density rises even higher in the core. Remember, this is still a gas. This is still a gas, and it's still gaseous because the temperature is so high, even though it's 20 or 30,000 times more, 10 or 20 million times more dense than water, and 10 or 20,000 times more dense than lead or gold. But this temperature finally allows oxygen to be fused into silicon, sulfur, phosphorus, and pretty much everything up until iron. Now, most of these reactions have enormous numbers of neutrinos because there's all sorts of many of the reactions create huge numbers of neutrons, which then decay rapidly. These rapid decay as neutrons then get captured and also create neutrons as well. So there's multiple different reaction processes that are happening in the star. I'm not going to really talk about the S process or the fast process or slow process, the RRS processes, because that gets even more complicated. But suffice it to say that the star, in these last days, the neutrinos losses are much more, there's more energy coming out of neutrinos than there are in light. Now it's building up a silicon core. So silicon is now building up, and this lasts for about a year. Finally, oxygen runs out. The silicon core contracts, and it heats up till it goes even higher in temperature and even denser, over 100 million times that of water, the density. And finally, when silicon burning occurs, the temperature is so incredibly hot that the silicon itself cannot withstand the intensity of the light that's there. The photons are so incredibly energetic at this temperature that they actually break the silicon apart into helium again and back down to protons and neutrons. So the silicon's getting destroyed by the light. And then the rest of the silicon is fusing into nickel and iron. That doesn't decay yet. This builds up an enormously heavy nickel and iron core, which will last only for about a day. So the temperature of the star, the luminosity of the star is incredibly large, but yet it only lasts a day. And here's nearly our finishing picture. At the end of this life of this supermassive star, more than 8 times the mass of the sun, there's hydrogen burning shells, helium, carbon, neon, oxygen, silicon, and all of these fusion shells where each layer is raining material down on top, from above, down below, as the pressure pushes it in. But yet down in the core, there's an iron nickel core, which is doing nothing. The size of the expanding envelope due to the instabilities happening down in the core is now bigger than the orbit of Jupiter, just like we see Betelgeuse being. And the reason for this iron nickel problem is what we call the nuclear impasse. Now, why are we caring about this? This is what's going to happen. This is why there's a big problem. When you fuse light elements together, you release energy. You release energy in the form of light, and you release energy in the form of neutrinos. But iron is the most tightly bound of those things. So you get energy by fusing light elements into heavier elements, so long as the elements are lighter than, have an atomic number less than 56, which is iron. So they release energy. But if you want to fuse elements heavier than iron, it must absorb energy. So once an iron core forms, there are no fusion reactions left for the star to tap in order to release energy. So gravity's still working, and that's what's happening. And here's a view of that thing again. Below iron, fusion will give off energy. Above iron, fusion takes energy, or more specifically, fission gives off energy. So that's why we use uranium in order to power our nuclear power plants, because uranium falls apart. And as it falls apart radioactively, it gives off energy. And that's what the far right-hand side shows. But we're talking about stars, we're talking about massive stars, and they all try to go towards iron, because iron is the most bound of all the nuclei. And if we look and zoom in really close to this binding energy, we find that it's specifically iron 56 and nickel 56, which are the most bound nuclei of all. And we see that this reaction network shows how much energy you get out, with the largest jump in energy coming from hydrogen up on the far left-hand side. When you start with hydrogen fusing to helium, that's the biggest step. When you fuse helium into carbon, notice the step from helium-4 to carbon-12 is really tiny. And then the step from carbon-12 to oxygen-16 is small too, but is much smaller. Again, from oxygen to neon, it's a teenier step. And so each step is smaller and smaller and smaller until you get to iron. So each step of this fusion reactions gives off less and less and less energy as it goes until you get to iron, and then it takes energy in order to fuse it, because that's what the curve means. So that's the end of the road. At the end of the silicon burning day, there's just an inert iron core with some nickel in there too, and there's this huge onion skin of burning shells all around it. And very soon, the iron core exceeds about 1 to 2 solar masses and begins to contract and heat up. And what it does at the end is final, catastrophic, and amazingly bizarre and wild. That's the end of the road for these stars. And stars between masses between 4 and 8 times the mass of the sun, they burn all the way up to carbon. And anything less than 4 solar masses only burns helium. And the cores of these intermediate mass stars become white dwarfs. Anything bigger than 8 solar masses gets all the way up to iron and does a catastrophic collapse. And what happens then, we'll talk about next time. See you soon.